Hello guys and welcome to this channel. My name is Roman Narvaez. I am a civil engineer with a specialization in structural engineering. Today we are going to go through a comparison about spread footing with Autodesk robot and of course with theme design. So we are going to look at bearing capacity analysis in soil for these simple spread footings. So to analyze spread footings for bearing capacity failures and design, then a way to avoid such failures, we must understand the relationship between bearing capacity, load footing dimensions, and soil properties. So we are going to look at these blue points about bearing capacity, simple bearing capacity formula, Terzaghi, Vesnik, Hansen, and ensemble. Okay, I switched to my iPad to open an application here. Here's the example that I am speaking about. We have a spread footing here with an elevation at depth of 1.50 meters. We have a load that's coming from the self-weight and the living load. We have thickness about 0.5 meters. And a plan view of this footing, which is square 1.50 meters by 1.5 meters. A column which is 0.3 meters by 0.3 meters. Some information about the loads here. We have the set weight of 50 kilonewtons. The live weight of 500 kilonewtons, and soil properties like density of this soil 18 kilonewtons divided by meters to the 3, density, saturated density of 25 kilonewtons divided by meters through the 3, a cohesive factor equal to 0, and a friction angle of 30 grades. To get inside this comparison, we need to go and look at some information here. For example, we can look at this differential soil here, a very little bit of the soil. And we have vertical stresses, normal stresses, and we have horizontal stresses in this soil. There is a relationship between these two, which have to do with the passive state of the soil. Resting earth pressure, which calls that name. We have a sand, for example, resistant earth pressure K0 equal to 0.3 to 0.5. We have clay from 0.5 to 0.8 and bigger than 1. Some very important concept about this differential soil is the shear understanding of this. So we have the vertical and horizontal stresses, but we have a capacity of shear for the soil, and this is expressed in the tau theta in this differential soil. To understand this, we need to manage quite alright a Morse circle and the stresses around that with the coefficient soil cohesiveness and the friction angle of this soil. What it means with this is that each soil has different friction angle. So for the sand that we are going to look, we have a angle of 30 grades. So we are talking about the formulas that is used to analyze these spreading footings in the soil. Terzaghi, and we have the other Hansen and Vesnik. So here are some considerations about form factors and other factors that we need to do that. But we can see here in this picture the contribution of the cohesion of the soil, contribution of the surroundings of this differential bit of soil, and we have the contribution of the cell weight and friction. All this stuff is managed with these parameters. Yes, of course, I show you here in my notes depth factors. We have this is taken for a book that I can give you the name later on. Ground inclination factors as well, and here is some groundwater effects as well. So the formula here that we are going to use, as you see before, is this one: shape factors, depth factors, load inclination factors, base inclination factors, ground inclination factors. All this stuff give us bearing capacity of this soil. Right. Okay, so for this purpose we can open the, for example, the calculation of this spread footing here with the geometry that I told you before, the width and the depth and we have the eccentricity as you told you before. So I prepared Excel list here for this first manual calculations that will give me some kind of information about, for example, the shape factors, depth factors, load inclination, and things like that. You have here some factors in the other here and as well. Here is the soil information, geometry information about the spread footing, and we have the geometry, of course, again, and the inclination factors and so on. Here is the formula for the calculation. With this, all this information, we calculate bearing capacity of this soil is approximately 1.12 megapascals. Afterwards, we have a safety factor of 1.36. So when we get into robot here, we can see the calculations. After giving these calculations, we have here the spread footings, and here is the information about the calculations for the bearing capacity. We have here 0.92 megapascals bearing capacity, and we have a safety factor around 2.2, which is bigger than 1. That's correct. A reference of the loads as well. This information we can compare with FEM design. Here is, for example, the soil that we're talking about. Here is the information about for example, the cohesiveness of this sand, which is 0. We have here 36 friction angle, and why we have this, I'm going to explain why. So if we look at this way to calculate in FEM design, they're using a safety factor here. So when you are given, for example, 40 degrees of friction angle, you put safety factors and you get a friction angle of 30.40. To make this, and this is the way that we use in Sweden, which in robot they use only directly without safety factors, and they get this information as you see that. So that's why it's a little different here. I have put in 36 the friction angle to make the same comparisons with the robot. And for the density, the dry density, and then the saturated density, I make some changes, little changes, to get exactly in the way that we have in robot. In that way, we have the soil here, and going to the calculations, we get inside these calculations, and here's the information about the geometry, the material, the soil properties, of course the combination load here, and which method we are using here in Scandinavia, the IAG report 7 2008, which is a little different. It's different in that robot is using. So we follow the old stuff that we have talking about the factors in the same way, safety factors. Soil factors. For what we're talking about was for contribution cohesion, contribution surroundings, and contribution of the cell weight and frictions. In that way, making these calculations and following this method with extra factors here, we have a bearing capacity of 1.3 megapascal, which is a little more than the robot. They have 0.92, and the manual calculation is 1.12. So we are in the nearby of these good calculations. So that is the way that we calculate the bearing capacity and of the soil. Okay, so I hope that you get more knowledge about structural engineering, and this is stuff is very important because all the superstructure that we have in structural engineering, like in, I show you here, we can call the superstructure, all that is over the soil is the superstructure. We are getting loads from this stuff, and with this we need to calculate the bearing capacity, if the house or the building is going to be there for quite a long time. We need to be sure that the soil is going to bear this structure. All right, guys, see you on the next time. Bye bye.